Alright, so for test 3, one problem that might show up on the test is a frames and machine type problem. I'm just going to do one on this review, but there are so many others, so many different types of problems, so many different supports, different connections. Make sure you know and understand them all. So here, determine the horizontal and vertical components of the force at pin, the pin at B, and the normal force the pin C exerts on a smooth slot. So C is not necessarily a pin. C is something inside of a smooth slot. There's a pulley at E, and of course this should be 50 pounds, not 50 feet. Also determine the moment, horizontal and vertical components of reaction at A. Okay, and draw 3-body diagrams, making sure all the forces are drawn in the correct direction. Now sometimes you might want to keep look at the whole free body diagram, but I think there'd be way too many unknowns. There's a BX and a BY, and then an AX, AY, and MA, 5 unknowns. So I don't think I'm going to start with that. I'm going to break it up, and if you're lucky, like I think we are, you can find a free body diagram that only has 3 unknowns. Don't necessarily expect that on the test. Sometimes, no matter where you go, you have 4 unknowns for one free body diagram, 4 unknowns for another free body diagram. Then you have to, solve 6 equations for 6 unknowns. But here, I think if you look at BCE, look at the free body diagram for BCE, we'll find that we have 3 unknowns. There is a BX and a BY. So here, BY, BX. There is this pulley that has 50 pounds and 50 pounds. Make sure you understand pulleys and know how to handle them. And then at C, there is a force that is normal to the slot. So I'm going to say there's this NC that is perpendicular to the beam. So the beam is at 3, 4, 5. This is going to be a 4, 3, 5 right there. So there's my free body diagram. If I ask for the free body diagram, like I'm doing right now, I want you to include the axes, X, whatever you're going to call X and Y, and maybe I shouldn't write those right down. I need to figure out what axes I want to use it for my X and Y. And then this would end up being something like, if it's a 3, 4, 5, this would be 5 feet, 5 feet, right there. All right, so I lucked out in that I had only 3 unknowns for that free body diagram, and I have 3 equilibrium equations, so I can solve. So summing the forces in X, BX, minus 50 pounds, and then minus the 4/5 component of NC, and the sum of the forces is equal to 0. Summing the forces in Y would be BY plus the 3/5 component of NC, and minus 50 is equal to 0. And then if I sum the moments about B, then BX and BY aren't in that equation, so then that will help things out. Now, don't overthink this. Just take that NC and multiply it times its perpendicular distance of 5. All right. Then take this 50 pounds times its distance of 6 feet, and that would be a negative moment, and then 50 pounds times 8 feet for the other one, and that would be a positive moment equals 0. So from here, we should get NC is negative 20 pounds. So NC is 20 pounds, and I want you to box in your right answer, and wherever you drew it, everywhere you drew it, draw it the correct direction. So now moving forward, I know that this is the correct direction on this free body diagram. It's 20 pounds this way, right, down and to the right. Now when I'm going backwards and plugging this in to find B, Y, and BX, I need to plug in that negative 20, right? I would get BX is positive 34 pounds, and I would get By is positive 62 pounds. All right, so now that I've got that, I can jump to my free body diagram for ACD. So let me think about ACD. It's fixed down there at A. So down there at A, it's going to have an AX, an AY, and an MA. I already know what's happening at C, right? It's equal and opposite, right? When you break two things apart where they're connected, make sure, BCE feels, whatever BCE feels, ACD feels equal and opposite that. All right, so let me draw a free body diagram for member ACD. Bring this up here. And let me draw this. All right, so there could be an AY, AX, and because it is fixed support, there could be an MA. I know that there's a 50-pound tension right there. Right, the rope tension is always pulling. And then the 20 pounds that I just found, right, let me go back to look. Oh, okay, goodness. Up here, right? Up here it was down and to the right. Okay, but down here it's going to be up, equal and opposite. So it will be up, and to the left. It's still at the same angle, 4, 3, 5. And then this is 20 pounds right here, acting right there. This is 4 feet. I didn't draw that too great. 4 feet. And here I have 1, 2, 3 unknowns I can solve for. So, include everything. If I'm asking for the free body diagram, include everything. And summing the forces in the x direction would be, I've got AX, I've got 50, and I've got going backwards 4/5 of that 20 equals 0. So AX negative 34. So AX is 34 pounds, so box that in. And draw this the correct direction. Draw this the correct direction. It is actually to the left. Everywhere I've drawn it, draw it the correct direction. That's the only place I've drawn it though. All right, summing the forces in Y would be AY, and it looks like that 20, the 3/5 component of 20 is going up. So AY negative 12 pounds. So AY is 12 pounds. Box that in and draw it the correct direction. And then my last equation, summing the moments about A. No matter where I sum the moments about, I need to include MA. I drew it counterclockwise, so counterclockwise is positive. Drew it counterclockwise. All right, so I've got MA. Let me go ahead and do that. 50 pounds, 50 pounds. Its perpendicular distance is 8 feet away. That would be creating a negative moment. And then, let me think about this. The 3/5 goes straight through A, but the 4/5 component of 20 is acting 4 feet away, creating a positive moment. Set that equal to 0, and we would get MA is positive 336 pound-feet. All of my forces were in pounds, all of my dimensions were in feet. It came out positive, so I don't need to change the sign or change the direction. All right, that's just one type of frames and machines problem. The one on the test will probably not be exactly like that. Look at some of the other ones. Look at ones where everything had 4 unknowns, and so you had to draw the free body diagram and the equations for one, draw the free body diagram and the equations for the other one, and solve for all of those. So look at all the different things you could do. Look at distributed loads. I could put a distributed load on there. Make sure you can handle those too. Okay? All right, so here's a problem where I want you to calculate the internal normal, shear, and bending moment at C. It says this force right here at P is 75 kilonewtons. All right, so I've got to be able to handle distributed loads, especially one that is a function. So hopefully you can remember that the magnitude, I'm going to do this pretty small, the magnitude is going to be the integral of the function, 30x squared, as the x goes from 0 to 2. So that would be 30x cubed over 3 from 0 to 2. That would be 80 kilonewtons. And it is acting at, let me see, it is acting at integral x f of x. So integral of x, 30x squared. So integral of 30x cubed over 80 that I just found. So the integral of 30x cubed would be 30x to the 4th over 4 from 0 to 2 divided by 80. Here we would get, the location would be 1.5, right? And I'm measuring from 0, right? 1.5 from here. So let me draw this as 1.5, right about here, 1.5 meters away. And I've got, if I'm replacing this distributed load with 180 kilonewton force. Make sure you handle distributed loads. All right. Before I cut this open, I want to find the reactions, right? Whether I'm looking at the left or the right, probably need to find some of those reactions. I think I'm just going to go ahead and find both of them. Sometimes you don't have to find all the reactions, right? Sometimes you can kind of take some shortcuts. But here, there's going to be an AY, and here at B, there could be a BY, there could be a BX. So looking at the whole free body diagram, and summing the forces in X, BX is the only thing in X, so BX is 0. Summing the forces in Y, we've got negative 80 kilonewtons plus AY plus BY and minus 75 is equal to 0. And then summing the moments, I think I'm going to sum the moments about A. I might should sum the moments about B. Doesn't matter too much in this situation. Summing the moments about A, let's see. I've got that 60 kilonewton meter moment. That one is counterclockwise, so that one is positive. And then I've got 80 kilonewtons acting 0.5 meters away from A. Remember, A is my pivot point, so that would be also a positive moment. The way I drew this, BY is acting 2 meters away from A, and it is also a positive moment if A was my pivot point. BX sort of goes straight through it. BX is 0, don't have to worry about that. And then 75 kilonewtons is acting 4 meters away. That one is a negative moment. Set those equal to 0. We would get BY is 100 kilonewtons. And plugging that back in up there, AY, I got to be 55 kilonewtons. All right, double check my work on this problem. I don't have a solution that I'm positive is correct. That's what I've got. Now I'm going to want to cut it at C and look at either the left side or the right hand side. You can do either one. You know, kind of looking at this, maybe I should have chosen the right hand side. There's only BY and P, but I'm going to choose the left hand side. Why don't you choose the right hand side and see if we get the exact same answers? Hopefully we will. But here I'm going to cut it and look at the left hand side. So cutting it. All right, so I'm cutting it at C, but I still have this 60 kilonewton meters. I have that AY, which was 55 kilonewtons. I've got that 80 kilonewtons right there. This is 1.5 away. This is 0.5 from there to there, and 1 from there to the cut. All right, so that's what I've got, draw everything that you see on there. And then when you cut it, we need to draw an N acting out, positive, a V acting down if I'm looking on this side, positive, and an M right there. Make sure you know and understand the sign convention. And if I know everything else, and those are my 1, 2, 3 unknowns that I can solve from the equilibrium equations from this section. Because this section, after I expose and open those internal forces, that section is still in equilibrium. So summing the forces in the x direction, again, I'm just going with my standard xy axis. Summing the forces in x, n is the only thing that's in x. It is equal to 0. All right. Summing the forces in y. Let's see. I've got, remember, y is up positive. I've got negative 80 kilonewtons plus 55, and then minus v is equal to 0. I'm going to get v. Let me be careful. V ends up being negative 25 kilonewtons. Remember, for this problem only, right, just for internal forces, if your answer comes out negative, I want you to leave it negative, okay? Because if we're all using the correct sign convention, we'll all get negative 25 kilonewtons, no matter whether I'm looking at the left side or the right side of it. And then I can sum the moments. I like to sum the moments about the cut. So summing the moments about the cut, I need that M no matter what point I sum the moments about. Let me go ahead and do that 60. That M was counterclockwise. This is counterclockwise positive. And the 60 is also counterclockwise positive. All right, but what else creates a moment about the cut? The 55 kilonewtons is acting 1 meter away, creating a negative moment. And the 80 kilonewtons is acting 1.5 meters away, creating a positive moment. Set that equal to 0, and I would get my M is negative 125, double check my answers here, kilonewton meters. I want you to leave it negative because we're all using the positive sign convention, so we're all going to get negative 125 kilonewton meters. Okay, so here's a problem that is finding the centroid of a function. So make sure you can do that. You remember the equation for centroids of a function. The x location is the integral of x tilde dA over integral dA. The y location is integral y tilde dA over integral dA. What is dA? What is x tilde? What is y tilde? That's what's pretty important about this problem. I would draw these vertical, pretend that's perfectly vertical. Let me try that again. Draw this vertical, not much better, rectangle, sorry. And this would be my dA, and the x tilde and y tilde would be the centroid of that rectangle. So the centroid would be x tilde, y tilde, and this, if you're doing it in the x direction with these vertical rectangles, then your x tilde is always going to be x. Your y tilde is going to be a little bit more complicated. I like to think of it as the average of the top and bottom. The top is 2. The bottom is 2x squared. And the average of those two numbers is, take two numbers, add them together, divided by 2. So I would say that x tilde is x, and I would say y tilde is, let's go and divide that by 2, 1 plus x squared. Okay? And that's what I can plug in here and here. My dA, I forgot to do the dA. The dA is the area of that rectangle. The area of the rectangle has a base of dx. It has a height of what? I would say it has a height of top minus bottom. Everywhere, no matter where I am on here, everywhere that height is going to be 2, and the bottom is going to be, the height is going to be 2 minus the bottom function, 2x squared. So there's my dA. So I can do all of these integrals. Now, do you see that this is symmetric about the y-axis? The centroid, I don't know, maybe the centroid is right here. If you see something is symmetric, you can go ahead and tell me one of those centroids. The x bar is going to be 0, all right? If you plugged in, and maybe go ahead and try this to double check me, if you plug in x tilde dA, if you plugged in everything right here, you should get 0. But not necessarily for y. For y, it's going to be the integral of y tilde dA over integral dA. So it's going to be the integral of y tilde is 1 plus x squared. So that's the y tilde. Now the dA is 2 minus 2x squared dx divided by the integral of 2 minus 2x squared dx. So then I just have to do the math. I need to do this carefully. Let me FOIL this. That's 2. That would be minus 2x squared, and that would be plus 2x squared. Those add up to 0. And then minus 2x to the 4th. All right, so that I haven't done the integral yet. I'm just multiplying that through. So when I do the integral of 2 right here is 2x. The integral of minus 2x to the 4th is minus 2x to the 5th over 5. And I need to evaluate this from, where do I need to evaluate it from? -1 to +1. Okay. And the denominator, the integral of 2x, integral of -2x squared, -2x cubed over 3. Evaluate this from -1 to +1. So plug in 1 here. Then subtract, and I'll do this. Plug in 1, 2 times 1 minus 2, 1/5 over 5. So that's what happens when I plug in, plug in 1. And then subtract what happens when I plug in -1. 2, -1 minus 2, -1 to the 5th over 5. Get that divided by 2, 1 minus 2, 1 cubed over 3. Make sure you subtract this whole thing to the right to -1 minus 2, -1 cubed over 3. All right. This, you would end up getting y bar of 1.2. Make sure you have units on x bar and y bar. Those were meters. Okay, so make sure you can do those centroids of functions. So here is an example of a centroid of a composite body. There's not a lot to memorize, right, in this for this test, or actually for this class completely. But, you know, the one we just did previously, centroid of a function and centroid of a composite body, they're very similar. Make sure you know this, or you'll have a hard time starting. X bar is summation of x tilde a over summation of a. The y bar is summation of y tilde a over summation of a. So I'm going to break this up into different sections. I'm going to say I have this quarter circle right here, section number 1. And then I'm going to say I have this large rectangle right here, section number 2. I'm going to say I've got this triangle right here, section number 3. And then I'm going to subtract out this half circle, section number 4. All right, and I like to make this chart to make it easier for me. Break it up into sections, section 1, 2, 3, 4. Write each one's area, each one's individual x tilde. Multiply x tilde times a, each one's y tilde, and y tilde times a for that. So if I can create this chart, that would be helpful. Move this up and fill this in. So for section 1, the quarter circle, the area is The area of a circle is pi r squared, and this is a fourth of a circle. The x tilde. Go to the sheet which has the centroids of different shapes. Go look at the centroid of a quarter circle. So you'll find that centroid of a quarter circle. Make sure you're looking at the centroid of an area, not the centroid of a line. But this would be 4r over 3 pi from there, and also 4r over 3 pi from here. So the x tilde is going to be 4, its r is 3 over 3 pi, and that is a negative x, right? Look at where my axis, here's x, here's my y, so that's in the negative x. So multiplying those together, x tilde times a, I've got negative 9. Looking at y tilde, its y tilde is 4, looking at that sheet, 4r over 3 pi, and that's in the positive y direction. Multiplying these together, I've got positive 9. Section 2. Section 2 is that rectangle. It's easy. The area of the rectangle, it's a 6 by 3. The x tilde from the origin, right? Here's the centroid right here. From the origin, it is 3 right there. The height, the base is 6, the height is 3. We kind of got the height from the radius of that quarter circle. So the x tilde is 3, the y tilde is 1.5, multiplying these together, 54, multiplying these together, 27. All right, the triangle, I've got that triangle, section number 3, the triangle, area of a triangle, 1/2, base times height. The x tilde, the centroid is right here, right? Break this up into thirds, break it up into thirds. It's a third closer to the left, a third closer to the bottom. So in the x direction, the x tilde, this is 1 right here, but remember from the origin, right, from the origin, it would be 7. Okay, multiplying those together, 31.5. The y tilde, from the origin, it is 1. And multiplying those together, 4.5. Then I'm subtracting out section number 4. I'm subtracting out section number 4, so I'm going to give it a negative area. This area is pi, let me be careful, its r is 1, pi r squared, but it's half of a circle, pi r squared over 2, and I'm giving it a negative area. Its x tilde, where is its centroid? Look at that, that handout, which will be stapled to the last page of your test, and you'll see that for the area of a half circle, it is it is 4r over 3 pi from there. But in the x direction, you see that it is symmetric, right? For the x tilde, you see that that is 0, right? Where's the centroid along the x-axis? It is at 0. Multiplying those together at 0. Here the y is 4r over 3 pi. Multiplying those together, negative 0.667. So to find the centroid, I need to sum the area, x tilde a, y tilde a. Here I've got 28.0, 76.5, and about 39.8. So the x bar would be 76.5 over 28. That would be 2.73 inches. That's x bar. The y bar would be 39.8 over 28. That would be 1.42 inches. That's the y bar. So that's my centroid. Make sure you can do centroid of composite bodies. Make sure you're familiar with that sheet of centroids of common shapes. Make sure you recognize the difference between a centroid in a line and a centroid of an area. Very important. All right, so this problem is using the theorems of Pappus and Guldinus to determine the surface area, including top and bottom surfaces and the volume. So I need to find the surface area in the volume of the solid formed by revolving the shaded area 360 degrees about the z-axis. All right, so first I'm going to do surface area. And I need to, not a lot to memorize, but I do need to know the surface area is theta RL, that the volume is theta RA, and I need to know what each one of those are. What is theta, what is R, what is L? So here, for the surface area, let's read the summation of theta RL. The volume is summation of theta RA. So what creates the surface area? So here's my rotating my z-axis. What creates the surface area? I would say that this top line, then this line right here, then this line right here, then this line right here. Those four lines, when I rotate them 360 degrees, or 2 pi radians, remember theta needs to be in radians, when I rotate them, that's what creates the surface area and nothing else. So I'm going to sum each of those theta RLs. So 1, 2, 3, 4. Those four lines create the surface area. So I'm going to say the surface area is theta RL for 1. So the theta RL for 1, the theta is 2 pi, goes a full 2 pi radians. The R, I'm going to come back to that. The L is a little bit easier. The L, that's just 15 inches. 15 inches. So the R, what is the R? The R is the distance from the rotating axis, the perpendicular distance from the rotating axis to the centroid. All right, don't overthink that. It's just the centroid of a line is at the center. And so its R would be 7.5. All right, so that's the theta RL for 1. The theta RL for another one, 2 pi. Its R, don't overthink it, it's right at the center, but its perpendicular distance from the rotating axis would be 15. Right, here's the centroid. It would be 15. Here's centroid of that one. Here's centroid of that one. Here's centroid of, those are all the R's. This would just be 15. And the length of that, what is the length of that line? 18 inches, right there, 18 inches. The next one, 2 pi, it's R. The center of that is right there. Don't overdo this, don't overthink this. If this beginning of the line is at 15 and the ending of the line is at 30, right? The beginning of that is at 15. The ending of that is at 30. Then halfway between those two is going to be my R. My R is at 22.5, the average of the front and back. Okay, so that is 22.5. Its length, I do kind of need to calculate this length. I've got this triangle that has a height of 20, a base of 15, a squared plus b squared equals c squared. This length would be 25. And then the last one, the bottom right here, the bottom, 2 pi. Let me go ahead and do the length of the bottom is 30. And the R for the bottom, the center of that 30 line would be at 15. Be at 15. So sum all of those up, and I would get the surface area is 8765 inches squared. Those units do work out. All right, so that was the surface area. Now I need to do the volume. If I were you, I would redraw the whole figure. I would not use this drawing right here to find the volume because you're using very different things. Right here, I used 4 lines, but for the volume, you use something different. So I'm going to clear this and redraw it to calculate the volume. So for the volume is summation of all these theta RAs. Theta RAs. So what creates the volume? I would say here's my rotating axis. I would say that the volume is created by this rectangle and this triangle. I would say that those two things create the volume. Maybe I'll draw this rectangle in blue and this triangle in red create the volume. So you see for the last one, for the surface area, I used 4 lines rotated 360 degrees. Now I'm using two very different areas. All right, so the volume is going to be summation of each one's theta RA. So let's look at number 1, this blue rectangle. Its theta is 2 pi. Its r, okay, well, where is the centroid? The centroid of a rectangle is easy. And so this would be the perpendicular distance. Just this, if this is 15, this is going to be 7.5. And its area, it has a base of 15, a height of 38. So that is the theta RA for that rectangle. All right, here's the theta, here's the R, and here's the A. And then for the triangle, I need to do its theta RA. Its theta is 2 pi. Its R, let me come back to, its A, it's a triangle. What is the area of a triangle? 1/2 base. It has a base of, let me think about it, it has a base of 15. It has a height of 20, and its R, all right, where is the centroid? The centroid would be right here, 1/3, closer to this side. So let's see, this is 15, this is 15, so it would be 15 and 5, so it would be 20 would be its R. So there I've got the theta, the R, and then the A for that one. So here, add those together, you'd get the volume of 45,710 inches cubed. That would be the volume. All right. So make sure you're ready for surface area and the volume for those theorems of Pappus and Guldinus. I think it's straightforward. Just make sure you on that sheet, whether you're looking at the centroid of a line or centroid of an area. One other thing, don't forget that the weight is the specific weight times the volume, right? In case I asked, instead of the volume, right, this is the volume. If I had asked for the weight, you could have found the weight for that problem as well. All right, good luck.